Hello again, welcome back to the latest lecture session. Today we are going to work out an example related to the design of let us say a particular contaminated matrix, let us say. Again, before we dig further, let us now refresh our memory with respect to the two approaches for solidification and stabilization, right. So, what are they? One was the case where we looked at the TCLP based approach, and the other is the risk based approach, right. Okay. So, in this context, what are the fundamental differences between both these approaches now? The example that we are going to look at today is the one related to the TCLP based approach, right. So, what is it that we are trying to do there? That we are trying to beat the test, right. As in why are we trying to do that? Obviously, because how is a particular waste classified as hazardous waste or such based on the TCLP test, right. So, we are going to design the system or matrix in such a way that, I mean, we will add the relevant fly ash, cement and so on and so forth, right, or different admixtures if required, and see to it such that we maintain a pH that is high enough such that even after addition of the acid in your TCLP test, right, you add acid in your TCLP test, I believe acetic acid, and we worked out the relevant calculations and it is around 2 milliequivalents per gram, right. So, even if we add that amount of acid, we will design it in such a way that the pH is high enough and the acid neutralizing capacity of the system is high enough such that the pH will not follow below that value, let us say, where let us say the solubilities of these heavy metals or the relevant compounds will be greater than the relevant standards, right. Again, we are going to try to maintain the relevant pH to be relatively high enough such that leaching is restricted, if I may say so, right. If not leaching, I guess I should not have used the term leaching. It is that let us say heavy metals which are precipitated, let us say or do not dissolve or such, right. Again, that is the aspect related to the TCLP approach. But what is this risk based approach about though, right. Again, this is the one that is relatively more stringent, and that would be that should be done, let us say, if I may say so, or that is a better approach certainly. And why is that a better approach? Because let us say TCLP approach, we are obviously trying to only beat the test, right. We are not trying to look at the actual site conditions or so on, which might be worse than what the TCLP is predicting, let us say, right. So, in that context, what do we do now? We look at a particular scenario or the site where this is going to be dumped and such, and we look at or consider particular D-observed or which will give you an idea about the rate of leaching, right. D-observed, I think this is something that we looked at based on D effective by retardation factor, right. More or less, what does this give you an idea about? It gives you an idea about the rate of leaching, let us say, or how fast or slow is the relevant leaching now, right. So, that is something that we looked at, and based on that, let us say, or we applied the material balance on that particular compound, let us say, right, and we looked at the relevant solution for that, right, and based on that we can come up with the relevant concentration, right, concentration of the contaminant in the leachate, right. So, let us say your leachate is flowing through, and now through the relevant matrix there is going to be diffusion or leaching into this particular what do we say leachate, right, and now this particular leachate is going to have particular concentration L of these particular contaminants, and which has a flow rate of QL. This comes in contact with the groundwater, right, which let us say can have some concentration of the relevant contaminants, and so after mixing, right, we are going to end up with C mixture and concentration of the and the flow of the mixture, right. So, based on again a simple mass balance, again we can now get what this concentration of the mixture is, right. So, once we know that, we can estimate what the exposure concentrations are for the relevant populations, right. Again, looking at the relevant risk based approach we did, which we looked at earlier in the class, right. We can calculate the different risks or potential risks, and based on that we can take a call, or one can take a call whether you need to look at other measures, or this particular solidification stabilization is good enough or not, right. So, obviously, this is the better approach. In this context, we were discussing about one particular aspect. Obviously, this is the concentration in the leachate, this is how we calculated that, or this is how we ended up with. So, how did we get this particular equation now? I think we had an equation for M total, right, and then took the relevant differential of that with respect to time, and then QLCl and so on, right. So, from that we have this equation. So, but let us just take a quick look of what this is giving us an idea about, right. So, this is the QL or the flow rate of the leachate, right, flow rate of leachate, yes, and what do we have M naught is the initial mass, let us say, that is fine, and L square will give us an idea about, let us say, what will it give us an idea about area available for leaching, area available for leaching. And as we mentioned or discussed earlier, depending upon is it a square or rectangular block, or is it spherical, or what is the kind of shape of your particular matrix, let us say. You can have different ways to calculate L square, right, and time is time, obviously, right. So, again, as QL or this particular leachate decreases, so you have this flow of leachate QL which is reaching the groundwater here, right. So, as this particular value decreases, right, what is going to happen? What does it mean more or less? That you have your block here and QL is coming in contact, right. If QL is less, what does that mean now? That the volume of water that is in contact with your particular matrix has enough time, let us say, for the system to reach equilibrium, right. But if QL is faster, right, what does that mean? That there is not enough time, let us say, for the system to reach equilibrium, and thus the system will be kinetically controlled. Let us understand that from point of view of this equation here. So, QL, as you see, as it gets higher, as the concentration, or pardon me, as QL or the flow rate increases, what is going to happen to CL? Obviously, CL is going to decrease, that is obvious, right. If you have some particular contaminant here and the flow rate of the leachate is increasing, let us say, right, the time it has for diffusion, let us say, is going to be obviously less, and thus the concentration in the leachate will be less, right. So, that is something we see, but it is not as if, let us say, if the concentration is what do we say, very high, let us say, what is going to happen in that case, let us say, or pardon me, not very high. In the other case, let us say, when we have the QL to be very less, right, as QL is less, CL obviously decreases, right. That is just the opposite of what we just discussed right now. As the flow rate, let us say, is relatively less, this volume of water in contact with your matrix has more time, and let us say now there is a greater concentration that will leach into your relevant volume of water. But it does not necessarily mean that as QL decreases much further, CL is going to reach infinity, right. It can't reach infinity, right. So, there is a threshold. So, what is the threshold? The threshold is going to be your equilibrium concentration, or the one, let us say, for solubility. Now, as you know, let us say, for each heavy metal or different kinds of heavy metal, there will be a maximum solubility or maximum concentration of that particular compound or metal that can exist in solution, right. So, that will more or less be your equilibrium concentration, let us say, for those particular conditions now, right. Obviously, if the conditions change, the concentration will be dependent upon the other relevant variables, but again we are looking at the equilibrium concentration to be threshold. So, in this context, we can look at this particular graph. What is this now? Let us say we have C here, CL, and log Q out here, let us say. What is the graph typically going to look like? It is going to be something like this, let us say, right. And obviously, from here on out, it is equilibrium controlled, right, all throughout here. Above this particular dotted line, it is equilibrium controlled, and below it is kinetic control, right. Let us just try to understand that. As Q increases, let us say, right, Q increases, right, what do you see with respect to C or CL, if I may say so? It decreases, right. And why is that? The system does not have enough time for the mass to be transferred from your particular matrix into the leachate. Now, that is what you see out here, right. So, that is what you see out here. But let us say if the Q decreases, what do we see? Obviously, that CL increases, right. But it theoretically, let us say, from this particular equation, it means that it should keep going up and up, or it can reach infinity, but that is not the case. So, the maximum is obviously going to have to be the C equilibrium, right. That is the maximum that it can go based on the physical characteristics at the of the site, let us say, or the water part, right. So, that is something to keep in mind, yes. So, now let us look at the example that we are talking about, or we have been referring to. So, that is again what is it now? Based on the TCLP approach, right. Let us look at that. So, first let us understand the question. So, we are going to design a mix right, solidification stabilization mix to minimize the TCLP concentration. So obviously we are looking at the TCLP approach for a sludge, okay, that is contaminated with looks like both lead and cadmium, okay, both are heavy metals, right. At what are the concentrations now? 5000 and 12,000 ppm, right, ppm is milligram per liter, right. So 5000 and 12,000 milligram per liter respectively, and hazardous waste characteristics as an of the TCLP test. Assume that you are to meet the hazardous waste characteristics levels of the TCLP. What does this mean? As in, let us say once I conducted this test, let us say I should be able to see to it that the relevant concentrations of lead and cadmium in that leachate, let us say in the TCLP, are going to be lower than the concentrations or the thresholds or the standards given in the 2016 hazardous waste and so on rules, right. So that is something to keep in mind, right. So that is what we are trying to say here, right. Assume that the mix should include the sludge. So it seems the options you have are Portland cement and fly ash, and one other factor obviously that helps you to solve the relevant system or solve for the relevant system is cement to fly ash ratio is 1.5. It can be based on, let us say, aspects related to the economy or the integrity or the structural integrity of the system and so on. So those two aspects typically determine how much cement to fly ash can you add and so on, right. So this is the relevant question. The take home message is I have both lead and cadmium at these concentrations and I want to beat the TCLP test, right. So let us understand what else we have here. So obviously we have the acid neutralizing capacity test, right. So we have that. Again, this can be presented either in the form of a graph or in the form of a table as we have now, right. So again, what is it that we are going to look at? As you add an acid, let us say you are going to decrease the pH, but it will give you an idea about the acid neutralizing capacity, let us say. So for cement, let us say do we have data at different pH, right. So at 13.4, and so obviously no what do we say, acid neutralizing capacity. But let us say what does this mean? Let us say 0 out here, and let us say I will go with 12 out here, 12 out here. So pH is 12 for in the cement column or the column relevant to cement, and 13.4 out here. So 0 out here. So what does this mean now? Let us just try to understand. It means that let us say 12 milliequivalent per gram, let us say, of the acid, or milliequivalent per milliequivalent of the acid per gram of the cement needs to be added to cement to bring down the pH from 13.4 to 12.0, right. So that is more or less your neutralizing capacity out here, or that is how you can understand this particular table anyway, right. So again similarly, let us say you have these particular values here, right, to go from 10 to 2.9 and so on, right. pH 10 to pH 2.9, the amount of acid that you need to add and so on. As you can see, here you need to add a base to go to, okay, here you have a value, negative value for this fly ash. So now let us move on to fly ash, right. So here we looked at cement and its acid neutralizing capacity and so on and so forth. So at fly ash 2 we have different cases, right. So let us say to go from pH 7.8 to 5.3, let us say we require 2 milliequivalents of the acid per gram of fly ash, right. But obviously as you see from in this region or at 10.8 you have value of -1 now, right. So what does that mean now? This fly ash itself, let us say is acidic in that particular region now, right. Or you can understand that in terms of the base that needs to be added to affect the pH out there, right. So that is something to consider that there. And same case with sludge, right. It does not have a acid neutralizing capacity obviously as you see in this particular range now, right. So it does not have an acid neutralizing capacity in that range. So obviously that needs to be taken into account when you are mixing both the cement, fly ash and sludge, that I guess sludge does not have any acid neutralizing capacity, or itself is going to consume acids, let us say, at these particular, or is going to behave as being acidic, let us say, at these ranges now, right. So again that is something to keep in mind. And what else? So and in the first aspect of this problem, right, 15% is dry solids, or the sludge is made up of 15% dry solids. So the question is, do we have sufficient water to completely hydrate the cement, right. And this is something that we looked at too, right. We need to maintain certain water to cement ratio, right? And we did look at one of the examples or minor examples that we looked at, right? We have to we can add additional water, or we can also see to it that the water in the sludge itself or the waste itself can be used to what we say hydrate this particular cement, and that's the aspect we are looking at here. Looks like the it's only 15% dry solids, and that will there be sufficient water, or do you need to add what we say more water to be able to get to a water cement ratio of 0.45, right? And the cement doses that we have calculated, right? Okay, let us move on and look at the relevant approach here obviously. So, obviously we need to be able to figure out the optimum pH, right? And in this case, as we just mentioned, we need to be able to balance out the concerns from both cadmium and lead. And as we know, let us say there is no particular pH at which, or one particular pH at which both cadmium and lead will both be at the relatively low concentration. So, let us look at the relevant graph. So, this is what we have here. This is the standard tables, let us say. So, solubility in milligram per liter, and keep in mind that this is the logarithmic scale, right? What does that mean? Let us say here it is 10 and here it is 1. So, 10 times, right? So, that means a unit of one difference here. If there is a difference in one unit, let us say, you can more or less neglect the lower value because it is 10 times lesser. And here we have pH obviously on the x axis. So, let us highlight where we are or what the compounds that we are looking at. So, this is cadmium, and that has a relatively low concentration at 11 or 11.1 maybe, right? And where is lead out here? Lead is somewhere out here. This is lead, right? And as you can see here, that I think comes out to be something like 9.25, 9 point something like that, right? 9.25 or so. So, now the key is which particular pH are you going to choose now, or what is going to be your optimum pH? As in, if I choose let us say 11, right, I can see that lead concentration is going to be considerably high, right. If I choose what we say the pH at which cadmium is going to be relatively low or the lowest one. And similarly, if I choose pH 9.25, I can see that the cadmium concentration is now going to be considerably high, right. So, obviously, there is in this case there is no one particular pH that will solve your issue, right. So, obviously, you need to balance it out. So, in this case, let us say maybe you can give greater weightage to the relevant compound, let us say, that is at higher concentration compared to its standard value, right. That is one case to go about it, or you can look at the ratio of the equilibrium to the relevant standard and look at trying to choose that particular case where the ratio of these two variables is going to be the same. So, let us look at what I have here. So, here looks like the concentration is in the sludge, this is what we know, 5000 ppm and 12,000 ppm. So, again here we have it in the units of, these are the standard concentrations from the TCLP, okay, that hazardous waste 2016 rules, and again 1 ppm, right. So, the relevant concentrations in the leachate after you do this TCLP test should not be greater than 5 ppm for lead and 1 ppm for cadmium, right. So, one way to look at this, to give to look at which pH to choose, is to look at the concentration in the sludge or waste to concentration or the standard concentrations, right. But here I see that both the ratios are the same, right, 5000 by 5 and more or less 1200 or 1000 by 1, more or less same, right. So, I can't really use this particular ratio. So, another ratio is, as we just mentioned, to look at the ratio of the equilibrium concentrations to relevant standard, let us say, right. So, let us look at that. So, at pH 9.2, as we discussed, it seems the concentration is around 8, pH 11.1, cadmium is so on and so forth, but we see we can't choose these pH values, right. So, the ratio of the equilibrium metal concentrations to their critical values are 5 and 1, right. 5 and 1 concentrations would be, where would they be same? Looks like they would be same near 9.6 though, right. What are we looking at? We are trying to balance out both the concerns here, and we are looking at equilibrium metal concentrations ratio to the critical values, right. So, around 9.6 looks like. So, let us move back to that particular figure. So, somewhere around 9.6, let us say, and let us say this is 9.5, 9.6. So, cadmium is somewhere out here. So, around 9.6, let us say. though it looks like the point of intersection, that's not that seems to be a lucky coincidence, if I may say so. But again, we are just trying to what we say balance both of them out as an equilibrium to the critical concentration. So you can either plot a graph, or or the ratio of cadmium to the relevant standard, and lead at equilibrium to its standard, and plot it and see the point of intersection, or you can try to look at it from this particular graph, right. Again, that's something to look at, and based on that, I guess we end up with the relevant pH to be around 9.6, right. So now that we have pH 9.6, what's the next step though, right? We need to be able to design the what do we say, different fractions. Let's look at what we have here. So obviously we are going to look at three aspects. One is the fly ash, cement, and sludge, or your waste here. So here right now we are not considering water here at this particular stage, let's say, right. So what are the different what do we say, equations that we already have? Because these are fractions, the sum should be equal to 1. So obviously the sum of all the fractions should be equal to 1. That's something that we have, and we know that the cement to fly ash ratio is already given at 1.5, right. That's under what do we say, independent equation. But obviously we have three variables and we need one other independent equation. So where do we get that from? Obviously that's based on the relevant aspects with respect to our particular case, which is the acid neutralizing capacity. So how do we do that? Obviously we know that we are adding 2 milliequivalents of acid per gram, right, in the relevant case of what do we say, the TCLP test, and this is what we need to be able to neutralize, right. So this needs to be the acid neutralizing capacity of your mixture, right, and that will be dependent upon the three fractions, let's say fraction into the acid neutralizing capacities of each of these fractions. So looks like we are almost out of time. So we'll look at these aspects, or we'll finish up this particular sum in the next session. But again, what's the crux here? What's one of the take home messages that we looked at here is that, as you see, just in the case when we looked at just two pH or two metals, pardon me, we could not, there is no what do we say, one pH value that we could choose, right. Obviously we had to look at different combinations or different ratios. One ratio was to look at which concentration was maybe relatively higher compared to its particular standard value. So to look at that, let's say, or when we looked at that, we saw that both the ratios for cadmium and lead were the same. So then we looked at the equilibrium concentration to the standard value ratio, and we arrived at a pH of 9.6, and we are looking at the relevant cases. So since I am out of time, we will continue this in the next session, and thank you.